All right, we left the last video with the question, okay, so we have the idea of countably infinite sets, those that have the same cardinality as the natural numbers. Is there anything else? That's what we want to think about here. So here's our theorem. There are other things out there. So the theorem is that R is not countably infinite. And another way to say this is to say that R is uncountable. Okay, infinite set, not countably infinite. All right, so our main goal is a proof of this result. This is what's known as Cantor's diagonalization argument. Okay, so it was given by the mathematician Cantor, late 1800s. So this result isn't even, or this proof of this result isn't even particularly old. I mean, as far as mathematics goes, late 1800s isn't especially early. But it's a neat argument, and we're gonna show that R is infinite but not countable, so uncountable. All right, so we're gonna do this by contradiction. So let's suppose for contradiction that R is countable. Okay, so in particular, R has to be in bijection with n, so it means we have an ordered list of real numbers. There is an ordered list of all the real numbers, and it looks like this. So the first real number on the list we'll just call R1, the second one we'll call R2, the third one R3, and so on. So we're going to construct a real number for ourselves. So let's construct a number A. All right. I'm assuming that all the numbers are written in all the numbers in the list are written in decimal form. So I'm going to let A look like this. It's going to be 0. These D's are just digits after the decimal place. So D1, D2, D3, and so on, where each DI is the digit in the ith decimal place. So when I say we're going to construct the number A, I mean I'm going to define what these digits di are going to be. So here's how we're going to do this. How are we going to define D1? I'm going to look at the first real number in our list. Okay, if R1 has a 0 in the first decimal place, then we're going to let D1 in our number A be equal to 1. And if R1 has a non-zero digit in the first decimal place, we're going to let our digit D1 be equal to 0. Okay, and that's it. And we're going to continue in this way. So I can actually write down sort of a general way to define DI. Okay, so what is DI? DI equals 1 if the ith decimal place of Ri is 0. So basically, I define each di here in the construction of the number a by looking at the corresponding number in our list of all the real numbers. So to define d2, I say, okay, well, let me look at the second decimal place for for R2. If that number is a 0, I'm going to put a 1. Oh, sorry, this is a di here at the bottom. So I'm going to put a 1. If it's a non-zero digit in the second decimal place of R2, then D2 is going to be 0. So 0 if the ith decimal place of Ri is not 0. Okay, so let's take a pause here and say, what exactly are we doing? Maybe it would help to actually write out something that illustrates how this number a is being constructed. So that's what we'll do next, just to give ourselves time to catch our breath a little and figure out, like, why are we defining di in this way, or what's the result when we define di in this way? Okay, so that's what's coming next. So what's happening here is a reasonable question. So here's the example. So let's say that our list of real numbers has this form. So the first number, let's say, is 82.4373. Okay, the second number happens to be 0.63719. The third number happens to be 0.000082. The fourth number is 1.11111, and so on. So these are all real numbers. It just so happens that we have our ordered list of real numbers, and maybe these are the first 4 in the list. So what does our number a look like, or what does the beginning of our number a look like, given this beginning of the list? Okay, so what would a look like? Okay, so we have the following. We have a is 0. I look at the first decimal place of the first number. It's 4. That's not 0, so I put a 0 there. I look at the second decimal place of the second number. That's a 3. So here are the ones that we're looking at. So we're looking at this decimal place here, second decimal place of the second number, third decimal place of the third number, fourth decimal place of the fourth number. That's how we're constructing a. So if I look at the second decimal place of the second number, that's 3. It's not 0, so I put a 0 there. I look at the third decimal place of the third number, that's a 0, so I put a 1 in that spot. I look at the fourth decimal place of the fourth number, that's a 1, it's not 0, so I can put a 0 there. And then depending on what else comes after that, right, we keep going. Right, so this is because the first decimal place of 82.4373 is not 0. We place a 0 there. Right, and then here the second 0 is because the second decimal place of 0.63719 is not 0. And then this 1 here is there because the third decimal place of this number, 0.000082, is 0. You put a 1 in that spot. Okay, so what is the upshot of this? If we do this construction in this way, the thing I want to notice is this. The thing I want to notice is this. A differs from the first number in the list in the first decimal place. Right? There was a non-zero decimal. There was a non-zero digit in that first decimal place in the first number, and I made the corresponding digit for A be 0. It differs from the second number in the list in the second decimal place, right? The second number has a 3 in the second decimal place, A has a 0. It differs from the third number in the list in the third decimal place, right? Our third number in the list has a 0 in that spot, A has a 1 in that spot. Right? And then it differs from the fourth number in the list in the fourth decimal place, because our fourth number in the list has a 1 in that decimal place, A has a 0. And we just continue in this way. So this is why we're constructing A in this way, because we want it to be different from every number in the list. So let's go back to our proof. So what we want to say is the following. First of all, we know A is in the real numbers because it has a decimal representation. I can tell you exactly what its decimal representation looks like. Right? I can tell you what each digit is going to be. So that means it has to be real. And notice it doesn't appear on our list. So notice A differs from R sub I, the ith number in our list, in the ith decimal place. So that's the specific location where we can guarantee our number A is different from a particular number in the list. But that means that A is not in the list. For every single number in the list, it's different from A in some decimal place. So then A is not in our list, contradicting the fact that our list contains all real numbers. Okay, and this means that R cannot be countable. Oops, R is uncountable. All right, so that's Cantor's diagonalization argument. Just construct this real number that can't possibly be in this list, this ordered list of real numbers, and it shows that R cannot be countable. So there is a different size of infinity here. Okay, so there's countably infinite, but then there's also uncountable at this stage. All right, just a little exercise I want to leave you with. So we said in our previous video that Q is a countable set. What if we tried to apply the same argument here from our proof that R is uncountable? What if we try to apply that same argument to Q? It shouldn't work. So the question is, why does Cantor's diagonalization argument fail when applied to the rationals? Right? It works on R, shows that R is uncountable. Why can't we use it to show that Q is also uncountable? I mean, we certainly shouldn't be able to do it because Q is a countable set.